Welcome to this video on meta-analysis. This video is part of a 3-day course on meta-analysis. For more information about the course, go to metaanalysisworkshops.com. For more information about the software, go to metaanalysis.com. Or send me an email at biostat100@gmail.com with the subject video. I'll send you a paper that explains the difference between the fixed effect and the random effects model and how to choose the correct model for your analysis. This is Michael Borenstein, and welcome back. At the moment, we're looking at analyses where the impact of treatment is essentially the same in all studies. The next analysis in this series is the Tamiflu example. Here, the outcome is continuous, and the effect size is a difference in means. The analysis I'll show here was published in Cochrane and was also published in BMJ. For full details of the review, please have a look at either of these papers. Tamiflu is a drug that's prescribed to deal with the flu. If a patient takes Tamiflu soon after symptoms appear, the drug should reduce the time until the patient begins to feel better. The analysis includes 8 studies. In each study, patients who had recently been diagnosed with the flu were randomly assigned to either of 2 groups. The treated group was given Tamiflu, and the control group was given a placebo. The researchers then asked the patients to report when they started to feel relief from symptoms of the flu. The researchers computed the mean time to relief in both groups, and the effect size was simply the difference in means. First, let's look at the data in Excel. As always, we don't need to use Excel. We can enter the data directly into CMA. However, I'm using Excel to show you how the data are structured. The data file in Excel is called Tamiflu symptomrelief.xls. Note that there are other Excel files for Tamiflu, so be sure to choose the right one. For those of you who want to run this analysis on your own, we have a PDF with the step-by-step instructions. I also have the Excel file with the data, and all of these are located at this website. The first column has the study names. There are 3 columns for the treated group. These give the mean time to relief, the standard deviation, and the sample size. The times are in hours. And there are 3 columns for the placebo group. These give the mean time to relief, the standard deviation, and the sample size. Now, let's create a file in CMA to work with this data. If you need a copy of the program, go to metaanalysis.com. Assuming that you have the program, start the program. If it opens with a tutorial, close the tutorial. I want to create a column to hold the study names. I'll click Insert, Column 4, Study Names. The program creates the column and puts it here. Next, we need to insert columns to hold the results from each study. CMA will allow you to enter the data from many kinds of studies, so we need to tell it what kinds of studies we will be using. Then, CMA will insert columns that we need for those kinds of studies. I click Insert, Column 4, Effect Size Data. The program opens this wizard. I can choose to work with common formats or all 100 formats. I'll choose all 100 formats, and then I click Next. There are 4 option buttons here. The first one is for studies that compare 2 groups. I'll choose that one and click Next. Here, the program lists 5 different kinds of data. The first is dichotomous data. I'd use this if the outcome was an event that either happened or did not happen. The second is continuous data. I'd use this if the outcome was the mean in each group. That's the case in our analysis, so I click on this row. Under the category where we compare means, there are various kinds of study designs. The first row is for studies that compare the means in 2 independent groups. The second row is for studies that use a crossover design with pre- and post scores for each group. The third row is for pre-post studies, and so on. In our case, the studies report means for 2 independent groups, so I'll choose the first row. To recap, we're looking at studies where patients are assigned to either of 2 independent groups, and the outcome is the mean in each group. For this kind of study, the data might be reported in various ways. The studies might report the mean, standard deviation, and sample size in each group. That's what we have, so I'll click on this row. When I select this row, the Finish button lights up. I click Finish, and the program creates the columns that I need to enter data in this format. For Group A, I have the mean, standard deviation, and sample size. For Group B, I have the mean, standard deviation, and sample size. And there's a column called Direction that we'll talk about in a moment. The program allows me to name the groups. It also recommends that I put the treated group first and the control group second. This is generally a good practice to follow, and I'll follow it here. I use the name Tamiflu for the first group. I'll use the name placebo for the second group. Now I'll click OK. The program applies these names. So for Tamiflu, I have the mean, standard deviation, and sample size. And for placebo, I have the mean, standard deviation, and sample size. I'll enter the data into the white columns. The program will compute the effect size and display that in the yellow columns. When I enter means for 2 groups, the most common effect size indices are the ones shown here. The standardized mean difference, sometimes called Cohen's d. The standardized mean difference with a correction to remove bias, sometimes called Hedges G. And the raw difference in means, called difference in means. We'll talk about all of these later. Now we simply want to use the raw difference in means. I could leave all of these here, but to keep things as clean as possible, I'm going to remove the 2 effect sizes that I don't need and leave only the one that I want to use. To modify any part of the screen, I right-click on that part of the screen. So I right-click on the yellow columns. The last item on this menu is to customize the display. I click on that, and the program displays this dialog box. There's a list of all available effect sizes. The check marks correspond to the 3 indices that I mentioned a moment ago. At the top, one of these has been selected as the primary index. This is the one that the program will use by default when we run the analysis. There are two things that we want to do. First, we want to change the primary index to be the raw difference in means. To do that, I click here and select Difference in Means. Second, I want to remove the other two indices from the display. To do that, I remove the check marks for these indices. Down here, there's a check mark for Also Show the Standard Error, and there's a check mark for Also Show the Variance. I want to make sure that both of these are checked. And now I click OK. The program is showing only the difference in means along with the standard error and the variance. At this point, I can enter the data. I'll flip back and forth between Excel and CMA. That way I can see the data and enter it into CMA. The first study is called M76 Double O1. I'll enter that into CMA. The name is M76 Double O1. For the treated group, the mean time to relief is 140.6 hours with a standard deviation of 125.2 and a sample size of 933. I'll enter that into CMA. The mean is 140.6. The standard deviation is 125.2, and the sample size is 933. For the control group, the mean time to relief is 165.5 hours, with a standard deviation of 156.5 and a sample size of 473. I'll enter that into CMA. The mean is 165.5. The standard deviation is 156.5, and the sample size is 473. There's a column here labeled Direction. If I click on this, the options are Positive, Negative, and Auto. I'll discuss these options later, but in most cases, I can simply choose Auto. This tells the program to take the mean in the first group minus the mean in the second group. So here, the mean time for the treated group is around 140 hours, while the mean time for the control group is around 165 hours. When we subtract treated minus control, the difference is negative, meaning that the treated group needed less time before the patients started to feel better. So this is what we would expect to see if the drug is working. For the first study, the effect is minus 24.9. This means that the treatment speeded up relief by around 25 hours or 1 day. I can enter data for the other studies in the same way. However, to save time, I'll copy the data from Excel. In Excel, I'll highlight rows 3 to 9. I'll click Control-C to copy. I'll switch to CMA. I'll click in row 2 under Study Names. I'll click Control-V to paste. The data are pasted into CMA, but the program cannot compute the effect sizes because the direction column is blank. I'll click in the direction column for the first study, which has been set to auto. I'll click Control-C to copy. I'll highlight the other rows, and I'll click Control-V to paste. Now I have the effect size for all studies. There's one more thing that I need to do. I'll click on Computational Options, Variance for the mean difference. The options here are Assume a common variance and do not assume a common variance. The program also tells me that RevMan and Stata use the second option. Since I'm trying to replicate an analysis that was published in RevMan, I'll choose the second option. But let me also take a moment to explain what these options mean. This is not something that's related to a meta-analysis. It's something that's related to the way that we analyze a primary study. When you run a primary study to compare the means in two groups, you always need to decide whether to assume a common variance or not assume a common variance. If you're working with a primary study and you're running the analysis in SPSS or Stata or SAS or any other program, when you run a t-test, you must tell the program which option to use. Now, all of these programs have a default setting, so if you don't specify which option you prefer, the program will use the default. So it's possible that you haven't thought about this in many years. But you did learn about it when you first learned about t-tests. And you are using one option or the other whenever you run a t-test. The basic issue is this. We get one estimate of the standard deviation for the treated group, and we get a different estimate of the standard deviation for the control group. These estimates are always different from each other. But are they different because of sampling error? Or are they different because the standard deviation in one population is actually larger than the standard deviation in the other population? If we believe that the standard deviation in both populations is essentially the same, and the sample values differ because of sampling error, then we should choose the option to pool the estimates. This will give us a more precise estimate of the common standard deviation, since this estimate will be based on more data. On the other hand, if we believe that the standard deviation is actually higher in one population than the other by a non-trivial amount, then we should not pool the values. Which option should we choose? I would generally look at what people did in the analysis of the primary studies and use that option here. I would also point out that the decision to use one option or the other is not likely to have a serious impact on the results. In any event, we're replicating a Cochrane analysis, and the only option in Cochrane is not to pool. So that's the option that we'll choose here. When I choose that option, the standard error and the variance for each study will change, but the effect size will remain the same. I'll click that option and click OK. At this point, I'll save the study. I'll click Save As. I'll name the study Tamiflu Symptom Relief. And I'll click OK. Now I'm ready to run the analysis. I click Run Analysis, and the program takes me to this screen. The effect size is the difference in means. If I wanted to choose another effect size, I would choose it here. The program displays a forest plot of the studies. I need to change the scale for the plot. I right-click on the plot and I choose Scale. The last item on the menu is Customized, and I select that. I'll enter a value of 100. This will give me a scale that goes from -100 to +100. After looking at this, I realize that there are two studies that don't entirely fit within this range, so I'll widen the scale. Again, I right-click on the plot, I choose Scale, I click Customized, I'll enter a value of 200. This works fine for me. Of course, the scale only affects the display it has no impact on the computations. At the bottom of the screen, I can select the statistical model. The options here are fixed, random, and both. For now, I'll select random. Later, we'll talk about why this is the correct model. As it happens, in this example, the two models will yield the same numbers, but it's still a good idea to select the correct model. Next, it's always a good idea to be sure that we understand the direction of the effect. Which group did better? In almost all the studies, the difference is negative. The outcome in these studies is time to relief, so a lower number is better. And since we're subtracting treated minus control, we hope that the treated group will have the lower number and the difference will be negative. I'll switch back quickly to the data entry screen to confirm that things are working as expected. For the first study, the mean is lower for the treated group than for the control group, and the difference is negative. So things are working as expected. I'll click Run Analysis to return to the analysis screen. I can see here that the effect size is less than 0 in all studies but one. So in most studies, the treatment reduced the time to relief. The row for each study displays the results for that study alone. For clarity, I'll leave out the negative numbers when talking about this. For the first study, the Tamiflu group reported relief around 25 hours sooner than the control group. But as always, the difference in the sample is only an estimate of the difference in the population. And it's the population that we care about. In the population from which this study was drawn, the difference probably falls in the range of 8.6 to 41.1. In round numbers, the treatment speeded up relief by at least 9 hours and possibly as much as 41 hours. That range, the confidence interval, excludes 0, so the difference will be statistically significant. Similarly, the p-value is 0.003, which is statistically significant. Similarly, we can look at the other studies. The results were statistically significant in only 2 studies. In all the others, the confidence interval includes 0, and the p-value is not statistically significant. This has no bearing on our analysis. I'm simply showing how we can get this information from the plot. Next, we can look at the line that shows the summary effect. The mean effect size is minus 16.759. Again, I'll speak about this without using the minus sign, and I'll use round numbers. In this set of studies, the treatment speeds up recovery by a mean of 17 hours. However, we don't care specifically about these studies. Rather, these studies have been sampled from a universe of studies, and we want to know the mean in that universe. The confidence interval is 25.101 to 8.418. So, in this universe, the mean difference is probably at least 8 hours, and possibly as much as 25 hours. Since this range excludes 0, the difference is statistically significant. And similarly, the p-value for the summary effect size is less than 0.001, which is statistically significant. We reject the null hypothesis that the mean difference is 0 hours and conclude that, on average, Tamiflu does reduce the time to relief of symptoms. I want to point out the similarity between the way that we interpret the confidence interval for each study and the way that we interpret the confidence interval for the summary effect size. Let's use the first study as an example. In this study, we defined a population, and then we drew a sample from that population. The effect size in the sample is 25 hours, But we don't care specifically about the 1,400 patients in the sample. Rather, we care about the population from which those patients were sampled. In that population, the effect size is probably somewhere in the range of 9 to 41 hours. Similarly, for the meta-analysis, we defined a universe of populations, and then we drew a sample of populations from that universe. The mean effect size in this sample of 8 populations is around 17 hours. But we don't care specifically about these 8 populations. Rather, we care about the universe of populations from which these populations were sampled. In that universe, the mean difference probably falls somewhere in the range of 8 hours to 25 hours. So, for any one study, we're generalizing from a sample of patients to the corresponding population. And for the meta-analysis, we're generalizing from a sample of populations to the corresponding universe of populations. To this point, we focused entirely on the mean effect size. Now, we need to ask if the impact of Tamiflu is consistent or if it varies. Is it the case that the treatment has the same effect for all populations? Or is it the case that in some populations the treatment has a major effect, in some it has a moderate effect, and in some it has only a trivial effect? Or even some where the treatment actually increases rather than decreases the time to relief. Why is this important? Well, it's important because it speaks to the potential utility of the drug. If the drug's effect is the same in all populations, then we can recommend the use of the drug in all cases. By contrast, if the drug is effective in some cases but not in others, then we need to know where it works and where it does not work before we can recommend it for use in any particular case. So how do we assess the heterogeneity of effects? As a first step, we can simply look at the forest plot. When I look at this plot, I get the sense that the effect size is pretty consistent across studies. Most studies seem to have an effect size within a pretty narrow range. But the effect size does appear to vary somewhat among these studies, and there are 2 studies with relatively extreme effects. So how much do the effects vary? To see the statistics, I click on Next Table. This table is divided into 2 sections. The section on the left deals with the mean effect size, and the section on the right deals with heterogeneity. First, let's have a look at the left. The statistics here are the same as the ones we saw on the prior screen. There's a row for the fixed effect model and a row for the random effects model. In this example, both models yield the same estimates, but we'll use the random effects line because that's the correct model for this example. The mean effect size is a difference of around 17 hours, and the confidence interval is 25 hours to 8 hours. In the universe of populations from which these studies were sampled, the mean effect may be as large as 25 hours or as small as 8 hours. Similarly, this range does not include 0, so the difference is statistically significant. Similarly, we can test the null hypothesis that the mean difference in this universe is 0 hours. The z-value for this test is minus 3.9, and the p-value is less than 0.001. We reject the null hypothesis and conclude that the mean effect is not 0. On average, across all relevant populations, the drug reduces the time to symptom relief. Now we turn to the right-hand side of the screen, which deals with the dispersion in effects. The standard deviation of effect is called tau, and it is estimated as 0. Let's think about this for a second. If tau is 0, then the impact of the treatment is exactly the same in all the populations that we studied. Common sense tells us that this is probably an underestimate because the impact of almost any intervention will differ from one population to the next. So while I'll use the estimate of 0, I'll assume that this is an underestimate. I assume that the effect size is similar, but not exactly the same across studies. The next question is, how did we estimate the standard deviation as 0 when it's clear from the forest plot that the effects do vary? Well, the answer is that the forest plot shows the variance in the samples, but we're estimating the variance in the underlying populations. Let's go back to the forest plot for a moment. Suppose that we had selected one population and then drawn 8 samples from that population. If the effect size in the population was 17 hours, then by definition, the population effect size for all studies is 17 hours. Would we expect the observed effect size in each of the studies to be precisely 17 hours? The answer, of course, is no. Because of sampling error, the observed effect size in some studies would be less than 17 hours, and the observed effect size in some studies would be more than 17 hours. Indeed, if the observed effect size in all studies was precisely 17 hours, we would assume that someone had fabricated the data. So, even if all studies come from the same population, we expect to see some variation in the samples simply because of sampling error. When we look at the forest plot, we need to ask if the amount of variation that we see falls within the range that we would expect to see based on sampling error, or if it exceeds that range. In this case, it turns out that we can expect to see this much variation simply because of sampling error. For example, note that the confidence interval for each study overlaps 17 hours. This holds true even for the 2 studies with extreme effects. In this study, the observed effect is 63 hours, but the true effect could have been 17 hours. In this study, the observed effect is 60 hours in the opposite direction, but the true effect could have been 17 hours in favor of treatment. So that's how it's possible that the standard deviation of population effects can be estimated as 0, despite the fact that the observed effects did vary. With that in mind, let's click Next Table and have another look at the statistics. Here we have Q and the degrees of freedom. Q is the sum of squared deviations on a standardized scale. It captures the deviation of every effect size from the mean effect size, but it does this relative to the standard error of that study. So, a large deviation is discounted if the standard error for that study is also large. The sum of these squared deviations is 6.325. The degrees of freedom is the number of studies minus 1. Here, that's 8 minus 1, or 7. As it happens, the degrees of freedom is also the Q value that we would expect to see if all studies were drawn from the same population. Let me say that again because it's important. Q is a measure of the dispersion that we actually see, and the degrees of freedom is the value of Q that we would expect to see based on sampling error. And that's the basis for all indices of dispersion. If Q is greater than the degrees of freedom, the dispersion that we see is more than we would expect to see based on sampling error. In that case, we proceed to compute the variance of effects. On the other hand, if Q is less than the degrees of freedom, then the amount of dispersion that we see is actually less than we would expect to see based on sampling error. In that case, we estimate the variance of effects and the standard deviation of effects as 0. In our case, Q is less than the degrees of freedom. So tau square is our estimate of the variance in true effects, that's 0, and tau is our estimate of the standard deviation in true effects, and that is 0. Finally, I² tells us what proportion of the observed variance reflects variance in true effects rather than sampling error. We'll talk about that later, but that also is 0. Later, we'll work with examples where Q is greater than the degrees of freedom, and I'll discuss these statistics in detail. In the current example, the message is simpler. There is no evidence that the effect size varies at all. So, when we talk about the potential impact of the treatment, we can assume that it will be pretty much the same for all populations. One last thing that I should point out is that these statistics appear on the line for a fixed effect analysis, but they actually apply both to a fixed effect analysis and to a random effect analysis. I'll talk about that more later. But for now, let's return to the main screen and look at a few more things. As I mentioned before, the fact that these two studies have very wide confidence intervals tells us that the estimates in these two studies are not very precise. First, let's understand why the confidence intervals for these studies are so wide. In this case, it's because the sample size in these studies is relatively low. If I click this button, the program will display the sample size for each study. For most of the studies, we have at least 200 people per group and relatively narrow confidence intervals. By contrast, this study has a sample size of 17 in one group and 9 in the other, and a relatively wide confidence interval. The same applies here, where the sample size in the two groups is 31 and 27. So that's why the confidence interval is so wide in these two studies. The next question is, what impact does this have on the analysis? Do we need to be concerned that these two estimates, because they are so unreliable, could have a harmful impact on the analysis? Well, the answer is no. These two studies, because they are so imprecise, get relatively little weight in the analysis, and therefore have little impact on the summary effect size. To show this, I'm going to click this button. The program displays the relative weight assigned to each study in the analysis. I can right-click on this column and select Scale Relative to Maximum. This will make it easier to see the variation in weights. This study gets about 26% of the weight. This study gets about 16% of the weight. This study gets about 20% of the weight. Let's jump down to the bottom for a moment. This study gets about 8% of the weight. This study gets about 16% of the weight. And this study gets about 12% of the weight. By contrast, let's return to the studies with very wide confidence intervals. This study gets about 0.5% of the weight, and this one gets about 1% of the weight. So these two studies together get less than 2% of the weight in the analysis. It follows that these studies will have only a very limited impact on the statistics, which is what we want. Let me click here to hide the column of sample size, and I'll click here to hide the column of weights. Now let's consider how we would write this up for a paper. I follow a pattern when I do this. I start with a short overview, then I discuss the mean effect size, and finally I discuss the variation in effect size. So the title is Tamiflu Symptom Relief. First, the summary. The analysis is based on 8 studies that evaluated the effect of Tamiflu on duration of flu symptoms. Each study compared Tamiflu versus placebo and reported the time to relief in symptoms. The effect size is the raw mean difference. So first we look at the mean. Does Tamiflu decrease the time to symptom relief? The difference in means is minus 16.8 hours. On average, Patients treated with Tamiflu reported symptom relief 16.8 hours sooner than patients treated with placebo. These studies were sampled from a universe of possible studies defined by certain inclusion-exclusion rules as outlined in the full paper. The confidence interval for the difference in means is minus 25.101 to minus 8.418, which tells us that the mean difference in this universe of studies could fall anywhere in this range. The range does not include a difference of 0, which tells us that the true mean difference is probably not 0. Similarly, the z-value for testing the null hypothesis that the mean difference is 0 is minus 3.938 with a corresponding p-value of less than 0.001. We can reject the null hypothesis that the drug has no impact on time to relief. Then we look at heterogeneity in effect size. How much does the effect size vary across studies? Well, the observed effect size varies somewhat from study to study, but a certain amount of variation is expected due to sampling error. We need to determine if the observed variation falls within the range that can be attributed to sampling error, in which case there's no evidence of variation in true effects, or if it exceeds that range. The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 6.325 with 7 degrees of freedom. Thus, the observed dispersion is actually less than we would expect to see by chance. It follows that there's no evidence that the true effect size varies from study to study. The I-square statistic tells us what proportion of the observed variance reflects differences in true effect size rather than sampling error. Since the variance in true effect sizes is 0, I-square must be 0. Tau square is the variance of true effect sizes, and here tau square is 0. And finally, tau is the standard deviation of true effect sizes, and here tau is 0. The next thing we might want to do is to create a high-resolution plot. The basic idea is that on this screen, I specify what columns I want to include in the plot, and then I click High Resolution Plot. I want to include only the columns that I really need, since every column takes up space, and we have limited space to play with. I click High Resolution Plot. Your plot may look a little different, so to get everything back to the default position, I'll click Reset All. Then I'll select Colors for Slides, and the plot should look like this. The text is relatively small. That's because we're trying to squeeze a lot of columns into a finite amount of space. So to increase the size of the text, I need to remove some of the columns. I'll click Return to Table. I'll right-click on the statistics. I'll select Customize Basic Statistics. I'll remove the check marks for standard error and variance. I don't really need those since I have the confidence interval. And I'll remove the check mark for the z-value. I don't really need that since I have the p-value. And then I'll click OK. Again, I click High Resolution Plot, and this looks a lot better. It's not obvious, but the plot includes a buffer zone on either side of the forest plot. This is to ensure that the plot stands out from any text. We want to keep the buffer on the left, but we don't need the buffer on the right. So I'll right-click on the forest plot. I'll select Spacing and Forest Plot Width. If you're using Windows 7, you may need to click on the bottom of this menu and pull it down to see the options. I'll click the tab for Right Buffer, and I'll click Remove. The program removes the buffer. This yields more room to play with, and the program increases the size of the text to to fill this room. Next, I might want to increase the spacing between the rows. I select the tab for row spacing. The red buttons will decrease the spacing, and the blue buttons will increase the spacing. One arrow means a small increase, and two arrows means a large increase. I'll click the blue button with one arrow 4 times. I don't want to increase the space too much, because if I put too much space between the rows, the text size will start to decrease. The plot looks like this. I'll right-click on the title. I'll enter the title, Tamiflu versus placebo, hours to relief, and I'll click Apply. I'll click the tab for font. I'll increase the font size by 1 click, and I'll close the menu bar. The two sides of the plot are labeled favors A and favors B. I'll right-click on the labels. I'll change favors A to favors treatment. I'll change favors B to favors placebo. I'll click Apply. I'll select font and increase the font size by 2 clicks. Down at the bottom, I'll right-click on the footer. I'll change the footer to read Random Effects Analysis, TOA equals 0. I'll click Apply. I'll select the tab for font and increase the font size by 2 clicks. I can save this as a WMF file and then pull it into any other program. To do that, I'd click File, Save As, WMF File. However, if I want to export this to PowerPoint or Word, I can actually do that in one step. I click File, Export to PowerPoint. On my taskbar, I see that CMA has opened a copy of PowerPoint, so I'll click on that. And here I have a new slide with the plot already inserted. If you're using an older version of PowerPoint, the plot will precisely cover the area of the slide. However, if you're using a newer version of PowerPoint, as I am here, the slide might cover more area than the plot. In that case, I can click Design, Slide Size, Standard, Maximize. And that takes me back to the original slide size. Incoming versions of CMA will offer the option to work with either size slide. In any event, I can save this file in PowerPoint, or I can copy the slide to another PowerPoint file using copy and paste. Next, I might want to export the plot to Word. I'll return to CMA. Under Color Mode, I'll select Colors for Printing. I'll click File, Export to Word. I'll switch to Word, and here's a new document with the plot inserted. So that's basically it for this analysis. My goal here was to show how the analysis works, but it's also worth taking a moment to put the analysis in context. We sometimes focus so much on the mechanics of the analysis and the test of significance that we lose track of our goal. So, for example, some have used this analysis or others like it to argue that the drug is effective. Tamiflu is effective in the sense that it reduces the time to relief. But the fact is that the impact is relatively modest. It reduces the time to relief from around 7 days to around 6 days. That's a pretty small difference, especially when we take into account that the drug has some side effects. But perhaps more to the point, If we're asking whether or not Tamiflu is an effective way to deal with an outbreak of the flu, we should not be asking about time to symptom relief. Rather, we should be asking about whether or not the drug reduces the risk that patients will be hospitalized. And we will look at that in a separate analysis. I hope that you found this video informative. This video is part of a 3-day course on meta-analysis. For more information about the course, go to metaanalysisworkshops.com. For more information about the software, go to metaanalysis.com. Or send me an email at biostat100@gmail.com with the subject video. I'll send you a paper that explains the difference between the fixed effect and the random effects model and how to choose the correct model for your analysis.